Hi students, welcome to week number 9 of operating system course. We are going to study memory management and we are going to continue with memory management. We discussed a lot about memory management in the last lecture, and we are going to continue with memory management in this lecture as well. I'm not expecting this lecture to be very long because we have discussed a lot of concepts in the last lecture, and the video was actually getting quite lengthy, so I had to stop over there. So I'm going to continue from there, and there are a few concepts left in memory management that are very critical, very important. So we are going to discuss them today. Some of them are algorithms, some of them are just the concepts like segmentation and so on, which are very famous. So we are going to go through those topics today. We are going to finish memory management today, and from next week we will talk about some other important concepts like file systems, security, and so on. So uh, before we jump into our topic, we are going to have a project as well. So I'm gonna allocate the project to you guys this week. So I will upload the project on Blackboard, and at the end of this lecture I'm gonna show you what the projects look like and what are the requirements for the project. So I have few projects that I have written for you, and you can come up with your own projects as well, but you have to get an approval before you start working on your own projects. So we need to have an agreement on that you are going for that project, and only then you can start working on those projects. So I'm going to get into more details when I talk about projects at the end of this lecture. So I'm expecting you guys to have done your assignment number 2 already. If you have not done that, please finish your assignment so that you can concentrate on your projects. You have around 3 weeks to complete your project. That I think would be sufficient, considering you have other assignments and projects as well. So I have made sure that the projects are not too comprehensive and they are not too lengthy for you guys to not be able to finish them in time. So I have kept that thing in mind as well, and I have chosen the projects in such a way that we have done at least some exercises of those projects, so that you have an idea how to go by your project. Since it's an operating system course, and we assume as instructors that when you are taking this course you have a good idea of several computer science concepts like discrete mathematics or data structures, object-oriented programming languages. So we expect that you guys already know those concepts, and based on that this course is built. So that's why you might have seen, in fact you have seen a lot of code in this course, a lot of other concepts that were related to maths, a lot of concepts that were actually related to the computing itself. So operating system itself has a lot of concepts that you might have not studied somewhere else, but the concepts like processes and threads, I mean they are core operating system concepts. Even the memory management, which we're going to say today, they are core operating system concepts. So that's one of the reasons some students think that this course is very difficult, because it comes up with a lot of new concepts. That happens with introduction to programming as well, by the way. I mean, a lot of students do feel that introduction to programming course is very difficult course, because maybe they have not seen a course like that before, and they are having first hand experience in programming. So operating system is pretty similar to that, because you might have not heard about a lot of concepts like deadlock and process synchronization or CPU scheduling and so on. So that's why it takes some time for the students of computer science. Although this is 300 level course, even then it will take you guys some time to understand those concepts. But once you understand these concepts, coming courses are not going to be very difficult for you, because by the time you study this course you have a good grasp of almost all the computing courses, and you are just going to move ahead with some of the topics. But you do have, when you go to advanced courses, I mean operating system itself is an advanced course, but if you move further you will see that at least you will have some idea of the concepts that you're going to learn in the coming courses. So that's why I have kept these things in mind when I was giving you projects. If you go online on Google and search for operating system projects, you will see some very large big projects students are doing, but I have not done that. I have kept in mind that we are going through a very difficult phase right now. This pandemic is not easy to go through. So I've kept all these things in mind. I'm going to discuss a little bit more about the project, but let me jump directly into the topic first. I'm not going to take too much time as normal. Normally our lectures are around 2 hours or more than 2 hours. So I'm not going to take that much time comparing to those lectures. I'm going to be very quick and going to leave you guys with some time to actually go through the previous concepts of memory management as well. So I'm going to continue from the previous topics of memory management. I'm going to quickly revise some of the important concepts that I am going to use in this lecture as well. So let's get started with memory management. So in memory management, we talked about pages. We have talked about a page fault. Just to quickly revise you that in our main memory is divided into different frames, and this is our RAM. So they are divided into different frames and they have addresses. Then we have our programs. So we have a program or a process. So we have a process P1. For example, P1 is divided into different pages. So different sections of the program or a process is called a page, and the size of each page is equal to the size of the frame. We discussed that, right? Now, since the whole program or a process cannot be kept into the RAM because of the limited memory size, we divide our process into pages, and those pages are then kept into RAM instead of putting the whole process in the RAM, right? So we know this, and this process is called paging, right? Dividing the process into different pages and fitting them into the frames of the RAM, they are called paging. This process is called paging, right? And then we talked about virtual memory as well. And virtual memory is basically space in your hard drive. So now, as we said last time, that RAM is very limited. Even though we have 16 GB RAM these days, even then it is very limited as compared to the type of processes we are running, type of pages we are running, and the amount of and volume of pages we are running at one time. You can anytime, go to, if you are using Windows, go to Task Manager, and if you are running Windows 10, it will show you the number of processes you are running and the number of threads you are running, and based on threads, imagine how many pages you might be running. So at any time, for example, or let me quickly show you that. So if I go to my Task Manager, if I go to performance, you can see over here. So this is the utilization of the CPU. Then there is the speed, and these are the processes. I'm not running too many things, by the way, currently, because I'm recording the video, so I normally don't run too many things when I'm recording. You can still see that there are 178 processes running, and there are around 2000 threads running, right? So there are so many things running right now, although I'm not running too many processes at the moment. So you can see that even when you are not running too many things, you end up having too many pages, too many processes and too many threads, right? So as I said earlier, we cannot keep everything in the RAM, so we cannot keep the pages of all the processes in the RAM. So what we do is we keep some of those pages in the RAM, and the rest of them we keep them in the hard drive, right? So we keep them in the hard drive, and few of them we keep them in the RAM, right? And whenever some of the pages are required which are not in the RAM, we bring them from the hard drive, right? So any page that is required by the CPU to process it, that is not in the RAM, we bring that from the hard drive, and this is called a page fault, right? This is called a page fault. If you remember, last time we discussed that if something that is required, if a page that is required by CPU is not available in the RAM, we have to bring that from hard drive, and this process is called a page fault, right? So page fault, we know about this. Now when something is not found in the RAM and we need to bring that from the hard drive, it takes some time for your system to bring that page. First of all, find that page in the hard drive, then bring that page back to your RAM. So it takes a lot of time. It's normally called a service time, right? It's called page service time, page fault service time. So it takes some time, and by that time CPU is just waiting. If there is no other process to be executed, CPU is just waiting, which means that we are wasting the time of CPU. So there has to be some good algorithm of which pages to remove from the RAM and which pages to bring from the hard drive. We know that we are going to bring pages that are required by the CPU from hard drive to RAM, but which pages to take out from the RAM, right? which pages to take out so that new pages can come into the RAM. So there has to be some way of doing that, right? And these are called page replacement algorithm, which pages to replace with the new pages, because RAM is limited, right? We do not have an infinite space for RAM to accommodate all the pages. We have limited space, and those spaces are already taken by different pages. So if a new page has to come, where that page has to come, right? For that we have page replacement algorithms. Okay, let's talk about them. So first of them is optimal page replacement algorithm. Normally what is happening is whenever you have whenever you have pages in the RAM, those pages are not always referenced. So if this is page number 1, page number 2, page number 3 and page number 4, these pages are not referenced all the time by the CPU. So CPU is not looking for all of these pages at the same time or all the time, right? It might need some of the pages after 100 instructions, some of them might be required after 1000 instructions, and some of them are not required until 1 million instructions, right? So computer will execute some of the code, right? So some of the lines of code will be executed by CPU. So maybe process 4 is required after 1 million lines of code, right? So it's not required every time, but this even 1 million instructions, because CPU is very, very fast, this is still this won't still take forever for CPU to be required, right? So optimal page replacement algorithm, what it does normally is it puts labels with the pages. So what is happening is normally, so if this is the page, let's talk about this. If this is the page number 1, in bracket we normally specify after how many instructions this page is required. So for example, page number 4 is required after 12 instructions, page 5 is required after 1000 instructions. Similarly, page 8 is required after 500 instructions, right? So let's assume that we have these pages in the memory and we are talking about optimal page replacement algorithm, and we have this situation in our RAM. New page comes in, page number 9, that is it is required after 15 instructions, for example. Now which page to take out from here so that page 9 can get in? Now we know that why page 9 is getting in, because CPU is looking for page 9 right now, right? So page 9 has to get in somehow, right? But there is no space for page 9 to get in the RAM, because all the spaces are allocated to other pages, right? In that case, what to do? Which page should be taken out from the RAM so that page 9 can get into the RAM inside your memory? So as mentioned by the optimal page replacement algorithm, any page that has the highest instructions in the bracket, it will be taken out, because this page is required now after 1000 instructions, right? It's not required now. So take this out and bring page number 9 in, so it will be replaced over here. Very, very simple algorithm. Next time if some page comes, next page that is required after the highest number of instructions, that will be taken out, which is page number 8 in this case, right? So any page that is required by the CPU will take place of any page in the RAM, in the memory, that has highest number of instructions. Now makes a lot of sense, because then you don't have to touch any other pages, right? All the other pages can still stay, right? Because this is required after 1000. Let's say that, let's replace instructions by seconds, right? So this page will be required from current time, it will be required after 1000 seconds, but this page is required after 1 second. So obviously we cannot replace this page, we cannot take out this page from the RAM, because then it will be required again after 1 second. Similarly, page number 3, can we take this page out? Yes, we can take this page out, but the problem is we have other pages that are required after this page, right? So this is again required after 10 seconds, but this page is required after 1000 seconds, for example. So better we take this out and bring in the other page, right? Instead of just taking this page out, which will be required again in 10 seconds. So better take out a page that is required after 10 seconds, right? So this type of algorithm is normally called an optimal page replacement algorithm. Now what is the disadvantage of this algorithm? The disadvantage of this algorithm is it's very difficult to implement. Theoretically looks pretty good, it looks like a very good solution, but practically it's very difficult to implement. Why it's difficult to implement? Because it's very difficult to know before we actually reference the page that how many instructions, after how many instructions this is this page is going to be required, because we don't know, right? We don't know. It's very difficult. We need to refer the page, we need to refer all the other pages before we actually get to know. So for example, if process 1 has 5 pages, for example, 3 pages for example, then we need to know how many how after how many instructions, for example, this page 4 is going to be required, right? We have to know this. So for one process we can know that, because for example, if this page has 100 instructions, this process has 100 instructions, and each page has 25 instructions, we know that this page is going to be required after 75 instructions, right? This page is going to be required after 75 instructions, right? Its turn will come. But when we are talking about different processes in the RAM, so there is not only one process, there can be hundred or thousands of processes, right? Thousands of processes. It's very difficult to calculate that when this specific process will be required, right? I mean, how many instructions, after how many instructions this page is going to be required. So that's why it's very difficult to implement it, because modern operating systems are very complex. They have so many different processes and threads running, and then those threads and processes are divided into different pages. It's very difficult to get this. So that's why the solution looks theoretically very good, but practically it's very difficult to implement this. The other page replacement algorithm is not recently used algorithm. So not recently used algorithm is, again, the problem is same, which is which page to replace to bring in a new page. So if memory is filled and we have a new page, which page should we take out to make a slot for the new page? This problem is the same one, right? So this algorithm we already discussed. The next algorithm is most recently used algorithm. In this algorithm, what we do normally is, for each page we have a reference bit and we have a modified bit, right? So there are going to be 2 bits for each page. If you remember, in page table entry we had reference and a modified bit, right? If you remember, you can pause the video here and go back to the previous video to page table entries, where we discussed there are different entries in a page table, and one of those entries was modified and the other one was reference. So these are 2 entries that are normally used. What reference does is, whenever a page is referenced, this R bit is set. Whenever the page is modified, this M bit is set, which means that operating system now knows that this page was recently referenced, or this page was referenced at least, or this page was modified, right? So it means that these 2 bits can tell us that these pages are modified and referenced. So it means that they might be referenced in future as well, because they were recently modified or they were recently referenced. There is a good chance that they might be referenced again, right? So based on these bits, we get to know that if a page has recently been used or not. So if it's not used, then these bits are expected to be zeros, right? If they are referenced, then they are expected to be ones. So this algorithm, not recently used, uses these 2 bits to get to know that if this page or if certain page has been addressed or not, or modified or not, right? So based on that, we replace the pages from the RAM. Now the next algorithm is first in first out, which means that just like what we did previously when we were talking about CPU scheduling, this algorithm does very similar things. So which means that pages are coming into the RAM. So let's assume this is our RAM. Pages are coming inside a RAM and they are maintained inside a queue which has a head and a tail. And in queue, we know from data structure that anything that is coming first will leave first, which means that first in first out. So anything that comes first will leave first, right? So it's over here. So this algorithm, what it does is, so assuming this, which means that P1 came first, P2 came second, and then P5 came last. So this means that this is the latest and this is the recent entry, the most recent entry, and this is the oldest entry inside the RAM. Now based on this algorithm, the page that came first will be replaced first. So if another page, for example P6 comes and CPU is looking for this page, which page to go out based on this algorithm? P1 will go out and P6 will take its position, because it says first in first out. Whichever page came first, it means that that page is the oldest one. It has been in RAM for the longest time, so it should be replaced and some other page should be given chance, P6. So this is how this works. But the problem with this algorithm is maybe P1 is referenced again. It's in high demand. This page might be in high demand, and after 1 millisecond it might be required again. In that case, what to do? but we have replaced it with P6, right? Because it was the first one, or the oldest one. But maybe P1 page is the one that has highest priority, and it might be required by the CPU again. So if we remove a page from the RAM and bring another page, which means that this page is going into the hard drive, right? This is going into the hard drive. We are taking it out from the RAM and taking it into hard drive. Now if this page is referenced after 1 millisecond, again it went to hard drive and straight away it has to come back, right? And this time is pretty bad. We don't need this. It's a hassle for the system. A lot of time is wasted over here, and we don't need that. So this algorithm might not do good when we are talking about page replacement algorithm. Having said that, this is one of the algorithms which is available that is used for page replacement algorithm. The next algorithm is second chance page replacement algorithm. What it does is it's basically an alteration of first in first out. What happens over here is, so if let's assume that this is a queue we have for first in first out, which means that this is head. Any process that comes first is, in this case, A came first, and this is the tail, which means that head came last. Over here what we normally do is we whenever we take a process from here, we put that at the end of the list, right? We don't take it to the hard drive, we don't put it in the hard drive, we don't do that. We put this at the end of the list, at the end of the queue. So if you see this diagram, basically process A has been taken out. For example, maybe a new process was about to come, so it was placed at the end of the list. It is placed at the end of the list, and maybe this new process came over here and it was processed. Why we are doing this? Because we are giving this process A another chance. So next time then process A is required, it is still in the RAM at the end of the list, and it can still be accessed. At least we don't have to go to hard drive and fetch the page from there. It is still in the RAM, but at the end of the queue. It is a little bit better than our first in first out, but again there is a problem that it might be required, but then other pages have to complete their turn first, only then A will have its turn, right? So this is the problem with second chance replacement algorithm. So the next one is a least recently used algorithm. It is actually based on optimal algorithm, and the assumptions are that the pages are heavily used, and if a page is used, it means that it might be used again, right? This is one of the assumptions. The second assumption is, if a page is not used up till now, it might not be used in future as well. It might not be used as frequently as the heavily used pages, right? For that we normally need a hardware, but I'm not going into the detail of hardware. Normally a register is required for that, but I'm not going there for now. What I'm going to do is I'm going to run this least recently used page replacement algorithm for you. Now let's assume this is our RAM, right? This is our RAM, and these are the frames inside our RAM, right? So these are some of the frames inside our RAM. Now these are pages. So this is page number 1, page 2, page 3, page 1, page 5, and these are how they are accessed, right? How they are required by the CPU, right? So this is what we are going to do. Now let's assume that the first page that came into the RAM is right now empty. There is no page inside the RAM. So first page came, so CPU said that okay, I need page number 1. So page number 1 comes, so since everything is empty, it will go over here, right? And what happens over here, by the way, before this page goes over there, CPU will ask for a page, and obviously operating system will look for that page inside the RAM first, right? If it's not in the RAM, if you remember, it's a page fault, right? Because we have to fetch that from the hard drive. So we'll say that it's a page fault. So page fault has occurred, and this page 1 is brought from the hard drive and placed inside the RAM. Okay, we are done. Next one. So next page came, page number 2. Page number 2 is inside here in the RAM. It's not in the RAM, which means another page fault has occurred, and this page 2 has to be inside the RAM, and it will be brought into the RAM from the hard drive. So we have one, which was our previous page, and now we have a new page, which is page number 2, right? So we are done up to page number 2. Page 3 came, same thing, page fault occurs, page 3 is not there. So page 3 will be brought from the hard drive. Page 1 is already there, 2 is already there, and 3 will be here. So I'm assuming that we only have 3 frames in the RAM. Obviously it's not, there are not only 3 frames, there are multiple frames, many frames inside the RAM, but just to make you understand this, I'm taking only limited number of frames. Okay, so 3 is also placed over here. We don't have any more space in the RAM. This is the maximum space. Only 3 pages can accommodate inside the RAM at one time. All right, this is what our system looks like right now. Okay, number 2. So page number 2 is accessed again. We'll check again. So operating system will check again. 2 is available inside the RAM or not. 2 is available, right? So it means that it's a hit. Remember, page hit and page miss, right? So it's a hit. We normally denote it with H, right? Denoted by H, sorry. So since 2 is already there, so I will say 1, 2 and 3, which will be the current situation of our RAM, right? They will remain like this, and CPU will process this page and so on, whatever it wants to do. Then we have page number 1. Page number 1 is inside the RAM. Yes, it is inside the RAM. So it's not a page fault, it's a page hit, right? So since we found it, so we keep it like this. We don't change it anymore. Then we have page number 5. So page number 5 is inside the RAM. It's not in the RAM, which means that it's a page fault. It's a page fault, right? So it has to be brought from the hard drive and placed over here. All right. So page 5 is brought from the hard drive, but where should we place it? Where should we place this page? Now, based on least recently used page replacement algorithm, a page that was least recently used. 1 was recently used. So we have only 3 pages. So 1, 2 and 3. 1 was recently used, so we can now replace it. 2 was also recently used. So 1 or 2 were recently used, right? We cannot replace 2. But 3 was the least recently used out of these 3 pages. So we will replace 3. We replace 5 by 3, right? So we are going to place 5 at the place of 3. So our new arrangement is 1, 2 and 5, right? 1, 2 and 5. And why we did this? Because comparing to other 2 pages, 3 was the least recently used. All right, let's move forward. So we have page number 2 now. Page number 2 is in the RAM. Yes, it's inside the RAM, so it's a hit, right? It's not a page fault. So we'll keep it like this: 1, 2 and 5. We have 1 now. 1 is inside the RAM. Yes, it is. So it's a hit again. We keep it like this: 1, 2 and 5. And CPU will come and access this page. We have 6 now. 6 is inside the RAM. 6 is not inside the RAM, which means that it's a page fault, right? So we need to bring it from the hard drive. All right, but which page to replace with 6? Which page to take out from the RAM so that 6 can take place of that page, right? All right, so we have to see which one was least recently used. Let's go back. We have to see from this point of time and go back and see. 1 was recently used, so we cannot replace it. 2 was also recently used, we cannot replace it. 5 was also recently used, but it is less recently used than the other 2, right? So 1 was recently used, 2 was recently used, and the most and the least recently used is 5. So we replace 5 with 6. We do 1, 2 and 6, right? 2 again. So 2 came again. 2 is in the RAM. Yes, it is inside the RAM. So we will have a hit here. We will have a hit here. 1, 2 and 6 will remain like this. Then we have 5. 5 is inside the RAM. No, 5 is not inside the RAM. So it should be brought from the hard drive again. Now which page to be replaced, right? Which page should go out so that 5 can take place? We go from here backwards and see 2. 2 was recently used, so we cannot replace it. 6 was recently used, we cannot replace it. 1 was recently used, but 6 and 2 were most recently used by the system, so we replace 1 by 5. So we do 5, 2 and 6, right? And obviously it's a miss, right? It was a miss because 5 was not in the RAM. Now next we have 5. 5 is inside the RAM. Yes, it is inside the RAM, so it's a hit. We keep 5, we keep 2 and we keep 6. Next we have 3. 3 is inside the RAM. No, it's not in the RAM, so we have a miss here or a page fault here. So which page to be replaced? We see 5 was recently used and 6 and 5 were recently used, and then 2 was used. So we'll replace 3 by 2. So we'll say 3 here and 6 here. We replace by 3. So next we have 1. 1 is inside the RAM. No, so it means that it's a page fault. Which page to replace? 3 was recently added and 6 was also recently added, so 5 will be replaced. So 1, 3 and 6. Next we have 3. 3 is inside the RAM. Yes, it is in the RAM, so it's a hit, and we keep the arrangement like this. This is how your least recently used page replacement algorithm works. Now if you see, I have some things over here. Now sometimes, well, majorly, you normally need to know how many times there were page faults. And normally in exam, if I bring a question, I might ask you based on this order using least recently used algorithm. By the way, I can ask this arrangement using any of these algorithms, right? Any of these algorithms. So in order to find a page fault, we just calculate how many page faults, we just count them, how many page faults occur. So 1, 2, 3, 4, 5, 6, 7 and 8. So 8 page faults occurred. How many hits occurred? 1, 2, 3, 4, 5, 6 and 7. So there were 7 hits and 8 page faults, right? So we need to use an algorithm normally where there are less page faults, right? This is the whole aim of using page replacement algorithm. So I hope you guys understand what page replacement algorithms are, why we use them, and how to use them, right? And why they are important. So next topic is design issues for paging systems. Now we know that we are using page replacement algorithms to replace pages so that we don't have to go back to our hard drive again and again. I mean, we have to go back to hard drive and bring new pages, but at least the pages that are referenced recently, we don't have to replace them, right? So there is when we are designing a paging system, we need to make sure that we don't have a lot of page faults, right? So in that case, we normally use two policies. One is a local allocation policy and the other one is a global allocation policy. Let me explain it to you with a diagram. Let's assume we have this situation in our RAM. So there are two processes. There are three processes: A process, B process, and C process, right? So A has these pages, B has these pages in the RAM, and C has these pages, right? For them, these are the processes, right? Now let's assume that we have a new page coming in, page A6. Let's assume A6 is coming. Now which page, since RAM is full, we don't have any free space, where should A6 go? At the slot of which page should it go? Now there are two policies that we can use. One is a local allocation policy. Local allocation policy means if this page belongs to a process, okay, so if this page belongs to a process, so this belongs to which process? Process A, right? It belongs to process A, right? Then this page can only take place for the pages of process A. Again, if we are replacing a page with any page in the RAM, that page, based on local allocation policy, we are talking about local allocation policy. Now that page A6 can only be replaced by the pages of process A. So we can take out a page that belongs to process A, which is for example A5 in this case, and place this over here. This is called a local allocation, which means that we are looking at only the local processes. We are not talking about the whole process. We are not talking about all the processes. Similarly, if process B, let's assume maybe B8, if page B8 comes in, this page B8 can only go at the place of pages that belong to process B, right? So it might go here and this will be page 8, for example. We cannot place B8 at the place of process A pages or process C pages. They have to go to the same process where these pages belong to. All right. So this is called local allocation. The other policy that we can use when we are designing the paging system is the global allocation. In global allocation, in contrast to what we did for local allocation, we don't look them as processes. We look them as pages, and we can replace any page with any other page. So for example, if B8 comes over here, I can go and replace C3 with B8, right? So I can replace B8 with C3, right? Or I can go and replace B8 with A0. It doesn't matter which process these pages belong to, and this is called a global allocation. So both of these policies are used in modern operating system, but just wanted to tell you that there are some policies that are used which are called local and global allocation policies. Next is the concept of thrashing, very important concept, and we already, by the way, know this concept. Now our RAM is has a finite space. We cannot place all of our pages inside our RAM, right? So we cannot do that. So this is our memory, this is our disk. So we cannot place all the pages inside our RAM. So what we normally do is we put some of the pages in the hard drive, right? And we keep only the required pages inside our RAM, right? Now what happens is our if our page faults, so what is a page fault? Page fault means that page was not found in the RAM and we have to go to fetch that page from the hard drive. So this is called a page fault. If a lot of time is being spent in addressing the page fault and less time is being spent by the CPU on running the pages, then this process is called, or this problem is called, thrashing, right? So what is happening is CPU is, for example, let's assume that there is P1, P2, P3 and P4. Alright, so CPU is first looking for P5. So it went to RAM and see P5, it could not find P5, so there is a page fault. So page fault occurred, right? So CPU has to wait because that page is not in the RAM, and any page that CPU wants to entertain or process, that has to be in RAM before CPU can actually go and process that. So let's assume that that page was brought from the hard drive and it's placed over here, right? And page 4 was taken back to the hard drive. Now after processing page 5, CPU is looking for example, page 6. It went to CPU, it went to RAM and searched for page 6, couldn't find it. So a page fault occurred. Page fault occurred again, right? And that page, and after that operating system has to bring that page from hard drive. So let's assume that it was replaced by page 3. So it was asked for, it was placed over here. So CPU will process this and it works. So while this page was brought from the hard drive to the RAM, CPU was waiting. So a lot of CPU time was wasted, right? Then let's assume that after that P4 was required. P4 was, and P3 is also here now. P4 was taken to hard drive. So now P4 has to come back to the RAM. So maybe P4 came here. But before that, since CPU couldn't find P4 here, a page fault occurred, right? So CPU had to wait. So what is happening over here is CPU has to wait a lot because there are lots of page faults occurring. So if a lot of page faults are occurring and CPU is not processing too much, just waiting for pages to be brought inside the RAM, this concept is called thrashing, right? One of the solutions to this problem can be we increase the size of RAM so that we have more pages here. So if we have more pages in the RAM, there is a less chance of a page fault, right? So this is one of the solutions, but this is very expensive because you have to buy the RAM, and even then you cannot have infinite size of RAM. RAM is definitely going to be a finite size. It can never match, it cannot be compared with the size of your hard drive, right? So we have to place at least some pages inside our hard drive, right? So this solution is not pretty good. To some extent it would work, but after some time we cannot keep on increasing the size of the RAM, right? There is another solution which is called a control load, and control load is exactly what we are doing here and exactly what we studied, right? We need to find solution, we need to find a way where hardware is not normally, I mean, I would not say hardware is not involved. We would say that we use some algorithms like what we did over here to make sure this efficiency of CPU efficiency is more. So there are less page faults and there are more CPU cycles, right? And how do we do that? We normally control the load. So what do we mean by controlling the load? By controlling the load means we have less page faults by keeping the pages, by keeping those pages in the hard drive that are not required too much, and keeping those pages in the RAM which are required too much. So we keep those, we swap those pages by using a very good technique, which is any of the algorithms that is performing based on what operating system we are using. So load control or using the optimal or using the algorithm that performs well can solve this problem. Obviously this thrashing problem cannot be 100% solved. It can be optimized, but it cannot be 100% solved. Page size, I'm not going to go through this because I've just covered pages and page sizes and you already know what an internal fragmentation is. So I'm going to skip this slide. I just wanted to keep it over here so that at least when you guys revisit these slides, you at least can read these, right? And you know what page size is, what an internal fragmentation is. But we have discussed in a lot detail what an internal or external fragmentation is. So I'm going to skip this. Now, the other policy when we are designing the paging system is the cleaning policy, right? When pages should be cleaned, how often pages should be cleaned. Now there might be pages in the RAM that are accessed. So for example, let's assume there are only place for 4 pages in the RAM. So we have these pages in the RAM, and they are all very high priority processes, high priority pages, right? And there is another high priority page, let's say P5, that also wants to get inside the RAM, right? So that it can be processed. Then in that case, which process should be taken out, right? Which process should be taken out? Now that depends upon the context. That depends upon that particular situation. At one particular situation, maybe P2 has the highest priority, and the other one still have the higher priority than the other processes, but P2 has the highest of all these priorities, right? Now based on this, these pages are replaced. Now cleaning policy, what happens in the cleaning policy is there is a daemon or a background service. Normally in Linux, background services are called daemons. A daemon is running, which is a cleaner process. It's normally at the sleep mode. What it does is it periodically wakes up and checks if some process is or some page is inside the RAM which is doing nothing and it's not required. So what it does is, what this daemon does is, it comes and takes that out and makes a space for the other pages, right? So not only on demand these pages are required, it creates an empty space here, so that if a page is required, it can go over there instead of just taking out that page that time, and it will take more time. So it will periodically come up, this daemon it will periodically come up and clean some space over there, so that if new process comes in, that has an empty space, and if a new page comes in, there is an empty space for that page over here, instead of when a page comes, then you have to take it out and then new page comes over here, which will take more time. So if there is already a space for a page, what will happen is it will quickly go to that place, it will quickly go to that address space, and that would increase the processing, right? And that would take less time for the processes to wait. So there will be less wait time for the processes. Then the last concept is the segmentation concept. I'm going to take this diagram to explain you, and as we discussed that paging is a very important concept. On modern operating systems they use paging, but some operating systems use segmentation as well. So what is segmentation is, for example, you have a program like this. So for example, you have this program, which is, you have a main method here, maybe you have function 1 here, you have function 2 over here. Now this main method is segment 1, this function 1 is segment 2, and this is segment 3. So your program is not divided into pages, they are divided into different segments, right? Now similarly, your hard drive is divided into different segments as well, right? Now those segments can increase or decrease pages. So your segments, so some of the segments in your RAM, let's take this example, some of the segments in your RAM, they have this much space, some of the segments they have this much space. So they are not fixed size spaces, just like our pages, they are variable size spaces. So if this is, for example, I have an example I guess over here, yeah, over here. So for example, if one of the segment is 7K, the other one is 8K, then 5K, 8K and 4K, and now if you see over here, we don't have enough space, right? But in some cases what we do is, this is a second scenario, for example. So for example, if we are looking at this scenario, it has segment 4 has this much space, so we have 3 KB of free space over here. So this is fine. If a new segment comes in which is not 3 KB, which is 4 KB, it still has to wait, right? So which is absolutely normal because there is no space. So what happens normally in segment is very similar to what pages is, just that it has variable sizes. So we don't have to fit all the pages in the same size, we can have different segments, and based on their requirement we can place them over there. So, and one of the important things that segmentation has is, it can use compaction to, for example, there is a free space here, there is a free space here, there is a free space here. It can combine all these free spaces and make a new bigger free space, so that if a segment comes in, it can rest over here. These are the things which normally pages cannot do, but segmentation can do that. So this is a quick visit of segment section. I'm not going to go into a lot of detail. It has a lot of detail. Segmentation has a lot of detail, but I'm not going into that detail because I think right now we have covered a lot of memory management, and if I cover a lot of other details as well, it's going to take us another lecture. So I'm not going to go there, so I'm going to keep it here. I just wanted to give you a brief idea of what segmentation is, but we have discussed in great detail what memory management is. We have talked about various very important concepts, and I think you have a good idea of what memory management is, how operating system manages your memory, how pages work, what are different algorithms. So we have spent good amount of time in learning what memory management is. So I'm going to close this chapter over here. I'm not going to go into further detail of what memory management is, what other things can we do with memory management. So I will stop it over here for now, and I think that's pretty much it for memory management. Now what I want to do is I want to dive into your projects. So I want to tell you what your projects look like so that you have enough time to work on your project. So I'm going to upload this file on Blackboard as well for the projects, and you know how to work with the assignments or projects. So I'm going to keep it like this. The deadline for submission of your projects is 29th of November, at the end of this month. So as I see right now, you have around 3 weeks easily. So yeah, somewhere around 3 weeks, which is good amount of time for your project. So you have to work in this file, so you have to put your solutions as always inside this file. Don't create a new file for me. I'm going to go through instructions in a while. And as I said that your projects are group projects. It's not a sole project, individual project. You don't have to do it alone. Please do it in groups. I would not accept any single guy doing project alone, because it's a group project. So we want to see how you can collaborate with each other. It's a difficult time, and this is how we learn also. If you're working from home in the industry, if you still have to work with the teams, how you can collaborate over the internet when you are online, right? So that's why we want to encourage you to be in groups and work in groups. Although you might be in different parts of world right now, you cannot go out, but you need to learn how you can communicate as team over the internet, right? That's why we have this group project. So in this group project, there is going to be a group lead. Maximum members in a group can be 3, minimum members obviously 2. There cannot be a single person in a group. So you have to decide who is going to be a group lead. You put your name and ID over here and decide who is the group lead. Obviously group leads name and ID will come here, and the other members will go over here, right? If you are 2 members, obviously you will fill the first 2 fields. So make sure you choose a group lead. And why you want to choose a group lead? Your group lead is going to interact with me, right? So you decide your group lead, and that group lead is, once you are done with your project, that group lead is going to submit that project. All right. So not everybody is going to go on Blackboard and submit their project. If there are 3 members in the group lead will go and submit that one project on behalf of every member of that group. So if there are 3 members in the group, I do not need 3 different submissions. Group lead will submit that project on his Blackboard, and I will take it from there. All right. So that's why we need a group lead. And I need to know from you guys your groups. So how many groups are going to be there, who is going to be the group lead, which project you are going to take. I want to know that by next week. So November 18, you need to send me an email. Each group lead is going to send me an email with the name of his or her group members and the project they are going to take. I need these 2 informations by 18th of November 2020. You can send me an email. Please send me an email. Each group lead is going to send me an email with the name of his or her group members and the project they are going to be working on, right? Maximum by November 18th. You can send it to me tomorrow. I don't mind. Send it to me tomorrow. But maximum you can take is 18th of November. If I don't receive an email from any of the groups, any of the students, I'm gonna put a group lead for them. I'm gonna give them a project, and I'm gonna assign a group for them. All right. So please send me your groups. Send me your projects. I mean, there will be one email from each group, and group lead is going to write that email, who's going to tell me that I am the group lead of this group. These are my group members, and this is the project we are going to work on. So this is what group leads are going to do. And there are going to be maximum 3 people in a group, minimum 2 people in the group, cannot be 1 person in a group. All right. So There are few projects I have written at the end of this document. I'll go through them very quickly. I'm not going to read all of them, but there is detail for each project written for you. You can go through those details. I'm going to go through only one project. So there are some projects in this document. You can take any of that project you like, or you can come up with your own idea. I don't mind. If you want to work on your own idea for a project, I don't mind that, but we need to talk about that first. If I approve that, then you can go ahead and work on that project. Why? Because it's a 30 marks project. I don't want to do something very minimal, and it will be injustice with other students, right? We don't want to do that. So there has to be equal workload on all the students when you're working on your projects, because it's a good number of marks associated with this project, right? It's 30% of your total marks. So make sure, if you are coming up with your own idea for this course, for the project of this course, please discuss it with me first. Once I approve that, then you can start working on that. All right. And since it's 30 marks and it's not going to be code, not everybody can code, not everybody is good in communication, not everybody is good in writing, right? So that is why this project is going to be 30 marks. Of course it is going to be 30 marks, but it is going to be combination of coding, it is going to be combination of writing report and presentation, right? So I do not expect a project that has only coding in it, right? I don't expect that, and that is not going to be the case, because we are going to have anyways some presentation at the end of this term, right? And I'm going to talk about that. So that's why wherever it is written to write a report, which some projects have, write a report for that. Some projects do not ask you to write a report. That is absolutely fine. If that is the case, then I am expecting that you are having only coding in that project, and then you are going to present that project at the end. At least 2 of these things are going to be in every project. So there are 3 things: coding, reporting, and presentation. So your project should have at least 2 of these things. You can have 3 of them, I don't mind, but at least 2 of these things are going to be in every project. So make sure you do that. All the details are available for each project inside this document. So I'm going to upload this document in Blackboard, and you can take this document from there and work on your projects accordingly. Please read these instructions very carefully. It's a project, it's 30 marks, and we don't want to lose any marks, right? So do not miss your username, your name and ID. So if a group lead is submitting this, I'm expecting, and there are three people in this group, I'm expecting 3 names over here, right? With group lead being at the top, right? So do not miss that. So it's a responsibility of the group lead, since he or she is going to submit me this document. You have 2 group leads. You have to make sure that there are names for all your group members over here, and your name and ID as well. Submit everything inside this document. So for example, you have coding, so all your code goes inside this document in solutions. If you have report, write everything inside this. So you might have a code over here, you might have on next page your report over here. I don't mind that. Everything should go inside this document. Please write everything inside this document. Don't prepare a new document for me. And I'm going to mark that according to what you submit in this document. If you are writing a report, make sure to reference. If you are taking anything from somewhere, please reference it and use APA style. We already know this because we are doing assignment number 2, almost done with assignment number 2. And this project is 30% marks, so make sure you do good in this. And I'm expecting only 1 submission. Not all students are going to submit this. Only group leads are going to submit on Blackboard. So group members are not required to submit their projects on Blackboard. So there is going to be 1 file by 3 people or 2 people, and group lead is going to submit that file for me, and I'm going to mark that according to the file you submit for all the 3 or 2 students inside the group. Submit that through Blackboard. Don't email me, please. We are not going to accept that email. So the deadline is 29th of November. You still have 3 weeks, and we are going to have a QA session or presentation session for you guys. And what I'm going to do is, hopefully in coming weeks, once I have received your names and groups and projects, I'm gonna create a session for you, for all of you guys, where each group will come online and we are going to have a presentation and QA session. So I'm gonna give you a day and a time where I would expect you guys to appear online, and we have a session. For each group there is going to be 15 to 20 minutes session with me. I will ask questions, you will present your project as well, and this is how we're gonna do it. So I'm gonna submit soon on Blackboard. I'm gonna put an announcement as well. I'm gonna upload a document as well that would contain the schedule of each group with time and date. We are going to have it on one single day hopefully and complete everything on that day. And if the time I'm submitting online, that would be maybe next week. If you think that time is not suitable for you and you might not be available on that time, it's absolutely fine. Don't worry too much. Just drop me an email, all right, and we'll find out another time for you. But we have to have this session because we want to make sure that everybody gets what he or she deserves, right? So we want to make justice for everybody. We don't want anybody worked nothing on a group, did not appear for presentation and end up getting good marks, right? This is injustice with other students. We cannot do that. So we have to make sure that everybody appears for the project, everybody has worked well on the project, and it will be very clear during the QA session and the presentation session, right? So please wait for me. I will submit once you guys send me your group names, group members names, your project names, and yeah, and these two things. I will put for you a schedule on Blackboard and you will get an announcement as well. And if you have any problems for that time, you are not available on that time, it's not suiting you, it's absolutely fine. Just drop me an email and we'll figure that out. This is the rubric I'm going to use. It's a bit different than your assignments. It has one extra thing over here. So anybody who has completed the project, they're going to get full marks based on how they have performed. Presentation based on your presentation skills and how much contribution you had in a project, you'll get marks on that as well. And then QA section, I'm going to ask you questions, and based on those questions you're going to get your marks, right? So each student in each group is going to get a chance to show his contribution, right? And you will be given marks according to your contribution, right? So these are the instructions. I'm going to quickly go through projects. So there are 3 projects, project 1, 2 and 3 in this document. Pick one project, let me know what the project is, and send me the name of the group members as well, and I'll put the schedule for you. So this is project number 1. It's called customized shell. Maximum number of students in this project can be 3, can't be 4, can't be 1. I should have written minimum, but I already told you that there can't be 1 student in a group. There can be 3 or 2 students in the group. And what you have to do in this particular project is you have to create a customized shell that we created during our exercises as well, right? Something similar to that, but it's a little bit more advanced. And what you have to do is whenever your project starts, you should have a prompt like this, like we normally have on our terminal, which says our name at the rate, the name, the desktop, for example, the name of your computer, it can be anything. So the name at the rate of your computer, and you should ask for commands over here from the user, right? So if user enters a command, that command should run inside that shell and display as the result. We did something like that, right? At least for the command part and the output part we have done that, but this thing we have not done. Now obviously you need to make sure that this project uses processes or threads. It's up to you how you want to work on that. But anything without process or thread, I'm not going to accept that. So you have each command should run in a separate project, separate process or a thread, which means that if I ask you to open activity monitor and you ran 3 different commands which are still running, then I should see 3 different processes in my activity monitor, right? And I might ask you to do that, because I will not ask you always to run me ls-la command, which is going to display something and then vanishes, right? It's not going to be like that. I'm going to ask you few commands to run, and I'm going to ask you to open activity monitor for me to show me that how that command is running and it's not interacting with the other processes, or it's not troubling the other processes or threads, right? So make sure you run that in different processes or threads. Your shell should be able to not only take commands, but it should be able to take some attributes, some parameters as well. So this is your command, we know that ls will run, but -la, will it run or not? Your program or your shell should be able to take parameters for that specific command as well. So if I'm talking about ls, it should run -l, it should run -a, it should run -la, and it should run maybe one more thing, right? So your command, your ls is your utility, right? Your utility or ls command should be able to run parameters as well, like -la or -a, -l, and so on, right? So make sure that your program, your shell does something like that. If it's running only ls, you might end up losing some marks, right? If it's only running ls-la, you might end up losing some marks, because it should run ls-a as well. It should run ls-l as well. It should also run ls-la, right? So something like that, which our normal shell does. Then your shell should be able to run a program from your computer. So for example, I have Firefox installed on my Linux. If I run a command Firefox, it should run Firefox for me. If I put Firefox, if I run a command like this, Firefox space &sign, then Firefox should run, but it should run in the background, right? So your shell should do something like this as well. So it should be able to run programs in foreground and background. How to run in foreground? I can just specify the name of my program and it will start running in the foreground. If I specify the name of the program along with &sign, that should run in the background. It should not run in the foreground. So you should be able to, your shell should be able to accomplish this as well. Now finally, your shell should run at least 10 shell commands. You can use ls, I don't mind. You can use cal, no, I don't mind. But you should run, your shell should run at least 10 shell commands, not only ls or cal or date or so on. You should run at least 10 shell commands. 10 shell commands, all right? That's why we have 3 students here. So you can split this into 3 commands each, right? It's up to you how you want to split it, but it should run at least 10 shell commands with parameters. It should be able to take parameters, right? At least 3 parameters for each command. At least 3 parameters. Let me write it over here. At least 3 parameters for each command. Right, so it should not only run with 1 parameter, it should have at least 3 parameters. So make sure you fulfill these. So this is how your projects look like. You have to do something like this. Then there are other projects that you can look into. I have provided all the details. Now while writing these projects, I have kept it very generic. I haven't given you the commands I want you to run. No, you can run any 10 commands of your choice, and I have made it very generic for you. If you read the description of other projects over here, you will see that they are very generic. So you have given so much liberty to work on it. You can add features to your project if you want. Otherwise you can fulfill these requirements and you are done. And they are not very lengthy at all. Some of them we have already done in our exercises. It's just a little bit advanced, just like what I showed you for shell. We have already done this, so at least 50% of the project you have already done that, right? Other 50% you have to work on. And there are other projects, and as I said, I have given you a lot of liberty on working on these projects. There are no specific requirements, very generic. For example, I've said in one of the projects, give me 4 client threads, so you have to make 4 threads only. So this is the requirement, right? So rest of the things, what do I need inside the threads, I have never mentioned that. I have not said that you need to use multi-dimensional arrays. I have never said that you have to use structs. I have never said that you have to use classes. It's totally up to you. I have never mentioned over here which programming language you should use. It's totally up to you which programming language, which features you want to use. It's up to you guys. It's so broad that you can program it in any way you like. That's why I have only 5 projects here. If some groups they end up taking the same project, it's absolutely fine for me, as long as they have implemented it in a different way. It's absolutely fine. And some of the projects like this one, for example, it has 500 words of report. You need to write a report. Just go through all these details. If you have any questions, just drop me an email, or maybe come and visit me in my virtual office hours and we can discuss about that project. But I have just given you very broad information about the project, and in detail you can go on to your own. If you don't want to add more features to it, it's absolutely fine. But we want to make sure that at least these requirements are fulfilled, which are very generic. And if you create a, for example, in one of the projects, for example this project, use different processes to develop. You have to develop 5 processes. So if you develop 5 processes, you get marks, right, for this point at least. So it's very generic, and I've kept it very broad for you. so that you don't end up I mean, we want to have students working on the project, right? So there are 3 students for each project, and the projects are not too big. When you start working on it, you'll get to know. But I want you guys to split these projects into 3 different people so that you can contribute. If you are a student that ends up getting the least amount of work, you need to talk to your colleagues, you need to talk to your team members that I won't be able to justify it, right? Because during the presentations, during the QA session, I'm going to ask you what is the contribution. Based on your contribution, you're going to get marks. And people who have done good, it's 30 marks, guys. It's 30 marks. Imagine getting 30 out of 30 or getting maybe 25 out of 30. It's good amount of marks. So please work on these projects. If you have any problems, anything you don't understand, please ask me, drop me an email or visit my virtual office hours, and we can talk about that. I'm gonna stop this video over here. I hope you guys understand the concepts. I hope the projects are not very difficult for you. If you want to further discuss, we can meet. Have a nice day, guys. Enjoy your time, and I will see you next week. Bye bye.